Thank you. What were we talking about last time? Do you remember? You say no. Sean, come on, man.
Geometric reflection.
I think we talked about both of those things. I think we talked about geometric optics and we talked about the law of reflection. What is geometric optics?
Using geometry to study the particle properties.
Ooh, that was well said. I like it. Can you say it louder so everyone can hear you?
You got it. Geometry to study the particle property of light.
Do you agree, Sam?
Yes. No, they do.
It's very non-committal. I don't know what to believe anymore. I think you're right.
Thank you.
I think it is using geometry to understand the particle-like nature of light. Because we talked last time about how light has a dual nature. It's got both particle-like nature and wave-like nature. And we can make sense of some things that light does in terms of these particle-like properties, and then other things that light does in terms of its wave-like properties. And we're going to start by talking about its particle-like properties, so we're going to use geometry to understand that better, right?
Yes.
Yeah, that's essentially what you said. Okay. But Sam wasn't listening, so.
Yeah, my bad.
It's all right. It happens.
We were talking about the MCAT.
That's a thing that you have to do, for sure. I'm going to do my part. I'm preparing you as best I can.
I appreciate that.
You know, it's what I do. We talked about the law of reflection as well. Somebody else said, is that what you said? Law of reflection?
No, I said.
Oh, you said that?
I said that. She said law.
Oh, now I'm all mixed up. So what is the law of reflection? It's not just a good idea, it's the law.
Goes in, goes out. With the angle.
Oh, okay, all right, there we go. So it is on the board behind me, so I hope you get it. It says that whatever angle that an incoming light ray hits with is going to be the same as the angle of the outgoing ray. The angle of incident equals the angle of reflection. All right, cool. And then we talked about how long a full-length mirror has to be. We used a little bit of geometry to figure that out, right?
Good.
That's, I think, brought us to the end of our time together. So that's all well and good. We're going to skip ahead a little bit because I want to continue talking about reflection a little bit more, and I want to talk about it in terms of a curved mirror. In order to do that, I have to go get my curved mirrors. Emily, can you go get the two gigundous curved mirrors? I'll try to stay in front of the camera as best I can.
Okay.
Actually, I'm going to be using the chalkboard, so Jake will reorient it if he needs to. So this is for a flat mirror. We talked about how the image produced by a flat mirror is equally distant behind the mirror as the object is in front of it, because your eye looks at light and sees it as going in a straight line, even though it doesn't in this case. It hits and bounces. So because it's bouncing off and coming to our eye, we see it as coming from a straight line and thus below or inside of the mirror. The mirror looks kind of like a window through the looking glass, right? Nothing? Yes? So, some response, some feedback. You let me know you're listening. Okay, a nod is, I guess, better than nothing.
Yes.
Okay, all right, cool. What if it's not a flat surface? When it's bumpy, we talked about what happens. The normal is constantly changing, right? What if it's not bumpy, but what if it is rounded? You're getting the other one too? Sweet.
I couldn't open the door.
No, that's fair. I'm not mad. I wasn't being mean. I was just asking. What if it's rounded like this? So imagine, if you will, a giant metal sphere. Let's say we take that giant metal sphere and we polish it up really good and make it shiny on both the inside and the outside, because it's a really nice metal sphere. And we cut a circle out of that metal sphere. That little section of the sphere would be one of these. If you're looking at it from the outside, it would be this one, where the middle part is closer to you than the edge. If you're looking at it from the inside, it'd be like this one, where the middle part's a little farther away than the edges. The edges are closer than you. The one on the right, this one here, that would be like looking at it from the inside, is called a concave mirror. Like a cave goes into a mountain, this is concave. The middle is a little farther away. This guy, we say is convex. The middle is a little closer to you than the edge. It's like looking at the sphere from the outside. All right. I've got my concave mirror and I shine a flashlight at it. I'm going to shine a flashlight so there are light rays coming in. Like so. What's going to happen to those light rays? You don't know? You have a guess? Well, it's a curve, and it's from a big sphere. So if I was looking at the cross-section of that sphere, it would be like a circle, right? And the normal of the surface of the circle is along the radius of that circle. Does that make sense? So if I make a circle with my arm, normal to the circle, the surface of the circle would be along my arm, always pointed along my arm. So in this case, the normal is radial to the circle. So if I'm going straight in, right at the middle of the normal is straight in. So that light ray is right on the normal, which means that the angle between the incoming light ray and the normal is 0 degrees, which means the angle between the outgoing light ray and the normal would be 0 degrees. So it's going to come straight back out. Light ray goes in, light ray comes straight back out. Up here, though, the normal is towards the middle of the circle, so the normal is going to be something like that, which means that there is an angle between the incoming light ray and the normal. So there's going to be an angle between the outgoing light ray and the normal, an equal angle. So it's going to come out something like this. The normal up here is going to be a little bit different. Everywhere it's going to be a little bit different because it's along the radius of the circle. So it's going to be maybe more like this, with a slightly bigger angle. So incoming light ray has that angle, outgoing light ray is going to have the same angle. Hey, look at that. This one, normal, angle, normal, angle. What's happening to all the light rays that come in parallel to that axis? What are they doing? Say what? They all meet at one point. They all come together at that one single point. We call that point, it has a special name, we call it the focal point. And the distance between the mirror and that point is the focal length. I don't know if this will reach. It reached. I brought with me some toys that you're going to play with in lab tomorrow. Going to turn the lights off for a second. Oh, turn all the lights off for a second. If you can't see this table, then stand up so you can see the table. Emily, can you see what's on the table?
Probably not.
Do you want to come so you can see it? Stand up. Come see. It's kind of fun. About why glasses work, probably next class or the class after. So coming in, bouncing off.
Okay.
Easy enough. If I turn this about a third of the way around, this side is a concave mirror. When I shine the parallel light rays into that concave mirror, they all meet at a single point. They all come together at that point right there, which is the focal point. A convex mirror, when I turn it a little bit more, causes the light rays to spread out, to diverge, as opposed to converging. So they spread out from a single point that would be behind the mirror, on the wrong side. This, when you see light bouncing off a mirror, we expect it to be on the same side as the light source because it bounces off, it comes back. This one diverges from a single point on the back side of the mirror. And we'll talk about the consequences of that today. So, concave causes light rays to converge. Convex causes the light rays to spread out. Have you ever shined light into a prism? White light into a prism? Do you know, I told you my rainbow joke, right?
Yeah.
Okay, so what happens when you shine white light into a prism? Say what? It spreads out, it turns into colors. We will talk about why that is when we talk about refraction, which is probably on Friday. But do you know you can put light back together? So you can take light apart and do its individual colors. Do you know you can put it back together too? Oh, okay, I'm glad you asked. So on this side, I've got 3 different colors. These are called the additive primary colors for optics, because those colors together, the wavelengths, when you mix them together, you can create any other colors that you want. If you put them all together at equal levels, we should get white light. So if I take my concave mirror and shine those 3 beams onto it, where they cross is a little spot of white light. Where only 2 of them cross, you can see yellow, you can see cyan a little bit over here, and you can see magenta. If I block one of these, we get different color combinations. Magenta, cyan. If I could block only the green, I think I get yellow in the middle. I don't know if I can block only the green. I can't block only the green. Dr. Treese has a really cool demo. Maybe he'll show it to you in lab tomorrow, where you can play with different colors. Pretty cool though. You can take light apart, you can put it back together, and now you have the knowledge to do it. All right, thanks for joining me, Amber. I'm gonna turn the light back on, heads up. Of course, not ideal.
Nope, not ideal.
If the angle of incident equals the angle of reflection, doesn't that also mean that the angle of reflection equals the angle of incident? It doesn't matter what order you put them in. So what if I shine my light ray not coming in parallel to the axis, but instead from the focal point going out? What would it do? Sydney? Yeah, it's going to come out the opposite way. It's going to just backtrack the same way. If this angle equals that angle, then if I'm shining light this way, it's going to go out that way. So if it comes in this way, it's going to go out this way. If it goes in this way, it's going to go out that way. So, have you ever seen this before? Answer, yes. When you, anybody ever change the headlight in their car? It's seated in a mirror, a mirrored surface, and it's actually parabolic. It's not spherical, because parabolic gives us a more cohesive beam. Doesn't scatter quite as much, but essentially the same idea. If you put the light source right in the middle at the focal point, and it's emanating light out in all directions, any of those light beams that hit the mirror from that focal point are going to leave as a beam, as a column, a collimated, cohesive beam of light coming out. A flashlight, same deal. Flashlights have the light source right at the focal point of either that parabola or the sphere. Fun fact, the focal point is halfway between the mirror and the radius of curvature, the center of curvature. So if I continued this circle all the way around, the focal point would be halfway between the center of curvature and the mirror, right in the middle. So we can actually use what I just told you, the information that I just gave you, to do a little bit of geometry and to approximate where images would be created by a curved mirror. I know there's images created by that mirror because I can see people in it. Right now I can see Cassie. If I move a little bit, I can see Allie. I can see people in there. I know there's images created. Images are what my eye interprets as what I'm seeing in that mirror. The object, this is just a little bit of terminology. The object is the thing that is either producing or reflecting the light that hits the mirror and goes to my eye. The image is what my eye perceives from that light. So, let's say I have a mirror. I'm drawing the mirror, I'm representing the mirror as a straight line because the curvature of the mirror is very, very small compared to the other distances that we're dealing with. And when you draw the curve in, it's exaggerated, which causes error in my diagram. Because the curve is so small, it is essentially straight up and down, but still has the properties of a curved mirror. So I draw it like this, but it is a mirror with a known focal length, f, like so. It's got a focal point, we know what it is. It could be 10 centimeters, it could be 8 inches, whatever, I don't know. It's just some number, we know how long the focal length, there it is, it's right there. It's Elena. That's you.
Okay.
I know, it's like looking in a mirror. Because it's a mirror. All right. I'm going to use the rules that I just gave you to draw a diagram that can tell me where the image is and what the image is going to look like of Elena in that mirror. So I can anticipate what I would see when I look in the mirror if Elena is standing that distance away from that mirror. Ray number 1, I'm going to draw from the top of her head. I picked the top of her head as a reference point because I could do this from any point on the object, and it's going to produce an image wherever those light rays meet from that point on the other side. So if I use left hand, I would just create an image of the left hand. But if I use the top of her head, I can, because the relative position of the rest of the points on her body are the same, that's a good reference point because everything else will be similarly positioned. I'll show you what I mean. I didn't say that very well, but I'll show you what I mean. So I'm going to draw a light ray. Light hitting the top of her head bounces in all possible different directions, which means one of those light rays is going to go directly parallel to the main axis of the mirror. And you know from what I drew right over here that any light ray coming in parallel to that axis is going to travel through the focal point. So it hits the mirror, bounces off, goes through the focal point. Another light ray coming off the top of her head is going to bounce off the top of her head, go through the focal point, and then hit the mirror. And you know from what I just showed you that anything that comes from the focal point and hits the mirror is going to leave parallel to the axis. So that's what it's going to do. And those two rays crossed, which means I already know where it's going to be, but I'm not a trusting kind of guy, and I might have made a mistake. So I always use a third ray just to check my answer. The third ray I draw is a ray that bounces from the top of her head and hits the mirror right at the axis. Right at the axis, the normal is along the axis, so the angle that it's coming in at will equal the angle it's going out at. Lo and behold, look at that, all three light rays cross at a single point. Now, terminology. When light rays actually cross, when they actually meet, we call that a real image. Those light rays came from the top of her head. So if my eye was observing these light rays, it would look like the top of her head was right here. So the top of her head is right there, with the rest of her body in a similar position relative to the top of her head. This is what I was trying to say earlier and I didn't say very well. So since the top of her head is there, and the rest of her body is oriented based on that position of the top of her head, she's going to look like this, which is upside down. We say that the image is inverted. If the image is upside down, it's inverted. All good? Okay. The distance between the object being seen and the mirror is called the object distance, DO. The distance between the image and the mirror is called the image distance, DI. So, the image that you see when you look in the mirror, based on what I just drew, should be upside down. And from what I'm seeing, a little bit smaller than you actually are. When you look in here, do you see you?
Yeah.
Are you upside down?
Yes.
Are you a little bit smaller than you actually are?
Yeah.
Cool.
So why is the bulk of light rays coming from the eyes? Or just because it's
Say one more time, I couldn't hear you.
like why is the one going to the X and one going below? Is it just because how it's farther down? Is that just why? I didn't know.
Can you point out what you're talking about?
I wasn't sure, like when you did the first line, not to the X-axis. Like why did you?
Oh, it goes through the focal point.
Okay. So why
And-
doesn't the other ones go through the focal points?
I'm going to go through the rules again real quick. There are light rays going from the top of Elena's head in all possible directions. I'm going to pick three that I know what they're going to do. And those are representative. If I used all of the light rays, if I took the time and drew a million of them, they would still all converge. They would still all meet. But I'm going to do 3 that I know exactly what they're going to do, so I don't have to do any measurements or other calculations. This one is going to go parallel to the axis. And light rays that are going parallel to the axis for a concave spherical mirror then pass through the focal point. So after it hits the mirror, it's going to go through the focal point. This one goes through the focal point. And I told you that if I send a light ray through the focal point, it's essentially just going backwards along the same track, right? It's going to leave parallel. And that's true for any of these going from the focal point. That's how flashlights work and your car headlights work. That's why they get a beam coming out. So this one goes through the focal point, and it's going to leave parallel. The last one I draw, just to check my answer, because I know they cross there, but I want to make sure that I'm right. The last one I draw hits the intersection of the mirror and the axis. And at that spot, the normal is along the axis, so whatever angle this is equals that angle. It comes out at the same angle, and that's where they meet.
And then what is the DO?
DO is the distance from the object, the thing that's providing the light to the mirror. DI is the distance to the image that's produced. That's kind of important because it has to do with how your brain interprets distances. I'm going to show you something. We're skipping ahead just a little bit, but because you asked that question, I want to talk about this now. This kind of mirror you've probably seen before, like in convenience stores up in the corner. They put it up there because the amount of space you can see in this mirror is bigger. You can see, when you look in this, you can see more of the room. But the stuff you see in the mirror is smaller. I'm going to draw some diagrams like this and show you why that is. But when your brain sees something as smaller, it interprets it automatically as farther away. We use this in movies all the time. It's called forced perspective. You put a little model really close to the camera and it looks like a giant. So that way you don't have to pay for like a giant model. You can make a little model and just put it closer to the camera than everybody else. Or you can make somebody look big if they're standing closer to the camera than the person they're standing next to. So because the image of you in this mirror looks small, you look farther away in the mirror than you actually are from the mirror. Have you ever heard this before? This sounds vaguely familiar to me. Object in the mirror is actually closer than it appears to be. Where have you heard this before? On your car mirrors. So the car mirrors are actually convex. They're actually bowed out a little bit because we want to get as broad of a field of view as we possibly can. But the consequence is that the objects are smaller, and thus your perspective of how far away they are is a little bit askew. Now, Elena, you told me, and I believed you. You have a trustworthy face. Like I've known you for a while now, and I trust you. You say you're upside down in here. You're sure of that?
Yep.
Okay, I'm going to let you take a closer look, and you tell me if it's still true.
Oh gosh.
All right,
I'm
so
not upside down anymore.
you're changing your tune, huh? Was it a lie?
No.
All right, Cassie, are you right side up or upside down? Are you? Let's double check. Are you 100% sure you're upside down?
No, I'm right side up.
Now you're right. I don't know what to believe anymore. I'm going to ask Sam. He seems like he likes participating. Right side up, upside down? Okay. Well, your eyes are maybe not so good. Let's give you a closer look.
Oh. Yeah, it's right side up.
Right. I don't know if it'll show up on the camera. Oh. Right side up, upside down. What, you're nodding. That was either or.
Right side up.
You're right side up? Nick? He disagreed with you. He thinks because he's wearing a suit, he can just say what he wants. Right side up or upside down?
Right side up.
Right side up or upside down?
I don't know.
I'm getting all kinds of different answers. Why is that? Oh, we changed the distance. And actually, if you pay really close attention, there's a spot in between where right now you're probably upside down. All right, and right now you're probably right side up.
Oh wow, that's really showing every detail on you. Holy smokes.
It's true, it does. But somewhere like right around here, you probably can't see yourself at all.
No, I can, but it's like I have double vision. Oh, I can still see myself.
Somewhere, upside down or right side
I
up.
can't see myself.
So
Now I see myself.
what's going on? You're right, it has to do with the distance. When you're upside down, I tend to be pretty far away. When you're right side up, I tend to be pretty close. And this point where you can't see yourself at all is kind of in the middle. And we only have one known value for this mirror. So tell me, based on that information, what you think is going on. Oh, well, 1, 2, go ahead.
Is it kind of like how a car works right now? Like, you know how like if the car gets in a certain line?
Oh, okay. I gotcha. So the blind spot in the mirror is more has to do with angles than this. This has to do with the nature of the mirror itself. Great thought though, because we talked about blind spots yesterday. That was clever connection. Same thing. Again, clever connection. Good thought. But not quite what's going on here, because the mirror on your car is actually convex, not concave. So let's do a little bit of an experiment. We have our axis for the mirror. We have our concave mirror. We have a known focal length. We did a diagram for when the object is outside of the focal length. Let's put the object inside of the focal length and see what happens. So there's my object. It's an arrow. It's not a person. I don't want people to get jealous because I'm drawing Elena the whole time. So, right?
Yeah.
So I'm going to draw my same rays. I'm going to draw a ray that goes parallel to the axis and then goes through the focal point. I'm going to draw one, well, I can't make one that goes through the focal point because it won't ever hit the mirror. But what I can do is I can say, what if it's coming from the direction of the focal point and continues out? That's on the same line, right? As if it was coming from the focal point. So it'll behave as if it came from the focal point. Since it doesn't really start here, it starts there, but it's going in the same direction as if it started there. And since straight lines are straight lines, it's no different than if I put the source at the focal point. So I can trace it backwards. I'll make it a different color just so you can see it. And it continues on. And it's going to behave as if it came from the focal point, which means it's going to leave parallel. And then my last ray, I'm going to draw to the intersection, and it's going to leave at the same angle that it came in at. Huh. Those rays that are leaving the mirror, they don't actually meet. It's actually kind of sad, isn't it? They started together, but then they diverge. They never meet again. They just kind of drift apart. A little sad story. But
like waves.
What's that?
Not like some of the waves.
Right. You know, it's not always a happy story. But if you trace it backwards, if you trace them to where it looks like they came from, because remember, your eye, it doesn't know the light bent. It doesn't know it bounced. It thinks that all the light that it sees comes from a straight line, from a direct straight line direction. So if I trace them backwards to where it looks like they came from, this one looks like it came from back here. This one looks like it came from back here. This one looks like it came from, whoa, look at that. They all meet at the same point right there. Producing, then I would have drawn it wrong. Producing what we call a virtual image. The light rays are not really crossing, but they look like they come from a single point. So when your eye sees those light rays, your eye interprets them as coming from a single point. And your eye interprets that as an image. And that image is right side up. So when I brought the mirror really close to you, you looked right side up. And what else is true about that image? Not only is it right side up, it's bigger, it's much bigger. We say that it is magnified. The magnification of an object is equal to the ratio of the image height and the object height. It's like the Seven Dwarfs singing their song about going to work. Hi-ho, right? If the image is way bigger, then you have a large magnification. If the image is smaller, you'll have a magnification that's less than 1. If the image is upside down, pay attention, this is important. If the image is upside down, then the image height is negative, and you'll have a negative magnification. So for this diagram over here, upside down image, smaller than the original, we're going to have a negative magnification that's less than 1. That one over there, it's much bigger and right side up. It's going to have a positive magnification that is bigger than 1. If it's twice as big, the magnification would be positive 2. If it's 3 times, it would be positive 3. Now, Sienna, you told me that there was a spot where you couldn't see yourself. Do you have any guess where that spot might have been for that mirror?
Where on the mirror?
So, in this case, you were way outside the focal point, and you were upside down. In that case, you're inside of the focal length, and you were right side up. So you blurred out when I went in between those two things. So where were you located compared to that mirror to make it so I couldn't see you at all? Cassie, do you have a thought? Let's try it. Let's find out. Let's see what happens when I have my mirror. She said it, but it was too quiet, so it doesn't count. Okay. Let's put the object at the focal point, and let's see what happens. I'm going to draw my same set of rays, except I can't draw them all. The focal point ray doesn't really work, but I can draw one that's parallel and then goes through the focal point. And I can, if I try to draw one that goes either to the focal point or from the focal point, it doesn't ever hit the mirror. So that one, it just doesn't work. But I can draw one that hits the mirror at the axis and then bounces off at the same angle. And those two rays, although I didn't draw them exactly perfectly, you'll find that they are exactly parallel to each other. This ray and that ray are parallel. The geometry makes them come out parallel, which means they neither meet anywhere, nor do they appear to have come from the same spot. They don't create an image at all. No image, neither virtual nor real, is created. Pretty interesting stuff. Part of your lab tomorrow is making diagrams like this for both lenses and mirrors. What if it's not concave at all? What if it's convex? Well, we still have our axis. Let's send a bunch of light rays in, all parallel to each other. I showed you what happened. I turned the lights off and I actually showed you down here what a bunch of parallel light rays are going to do. What are they going to do? Were you paying attention? I told you to come down and look. Say what? They're going to diverge. They're going to spread out. The one that hits right at the axis is going to go straight back. The one that hits here is going to go out a little bit. The one that hits here is going to go out a little bit more. The one that hits here is going to go out a little bit. The one that hits up here is going to go out a little bit more. And they just spread out. They get farther and farther away. But if I trace them backwards, they all meet at a single spot. This single spot right here, where all of those incoming light rays diverge from, is called the focal point. Yeah? Your eye uses lenses, not mirrors, but similar. Actually, believe it or not, it works more like the concave mirror, but this is the process that your eye uses to create an image. We're going to talk about that in some depth. Because the light rays are bouncing off and diverging, but not actually meeting, the focal point is kind of sort of on the wrong side. We would expect them to focus on one single point where the light rays actually come together, but they don't. They just appear to come together. So we say that this has a negative focal length, minus f. It can still produce images, and we can still find them with our ray diagrams. But it won't produce real images, at least not by itself. If you put it in combination with other things, you can make real images, but it won't make it a real image by itself. Regardless of where I hold this, you'll always be right, but I'll never be able to project that image onto a screen. It just won't work, because it only produces virtual images. The process for my ray diagrams is very similar. So I'll have a negative focal length, a convex mirror. I've got my object somewhere in front. I can draw a light ray that goes parallel to the axis. And it's going to leave directly away from the focal point. If I send a light ray towards the focal point, as if it was going to hit the focal point, if I continue that on, it would hit the focal point, it's going to leave parallel. And if I send a light ray so that it hits at the axis, it will once again leave at the same angle that it came in at. Those three light rays will never meet. But I can trace them backwards to a single point. Trace backwards, and they all appear to meet at this single point right there. Describe the image for me. Use my terminology. Is it real or virtual? Do the light rays actually cross?
No.
So is it real or virtual? Virtual. Is it upright or inverted? Upright. Is it bigger or smaller? So it's got a magnification bigger than 1 or smaller than 1? Smaller than 1. It's got a positive magnification smaller than 1. So we have a virtual upright image with a magnification that is positive and less than 1. Look at yourself in the mirror. You are seeing a virtual image of yourself that is upright and smaller than you, just like we anticipated. For both of those, we can use something called the thin lens equation. Yeah, I know they're not lenses, but the equation still works. The mathematical equation to associate the image distance, the object distance, and the focal length looks like this. 1 over f equals 1 over di plus 1 over do. That's called the thin lens equation. In lab tomorrow, you're going to prove it for both lenses and mirrors. Lenses use refraction, which we haven't talked about yet. Mirrors use reflection, which we've spent the last 2 classes talking about. Yes. The difference between concave and convex is that one has a negative focal length and one has a positive focal length. For a virtual image, this is also important. I don't think I mentioned it, but I think I need to. A virtual image will have a negative image distance because it's behind the mirror. The distance in front of the mirror is the image distance. If it's behind the mirror, it's a negative distance. So convex mirrors have a negative focal length. Virtual images have a negative image distance. It is possible to have a negative object distance, which you will discover in lab tomorrow, I think, if you're doing the geometric optics lab. But we aren't going to talk about that today. Dr. Treese will have to talk about that with you. I gave you half of the magnification equation. There's actually a little bit more to it. Magnification is the height of the image divided by the height of the object. But you can also find it based on the object distance and the image distance. It also equals the negative image distance divided by object distance. Those are both equations for magnification. You could use this equation or that equation. All right, so to recap what we've talked about today. we refreshed our memory on reflection. And we said that we've talked about flat mirrors, but what if those mirrors aren't flat? What if they're rounded? What if they're curved? In this case, what if they're spherical? We don't, so I got to visit a power plant in Sicily. It was a solar power plant that had huge parabolic mirrors. And in the middle of, at the focus of that parabolic mirror was a tube of water. And the parabolic mirror would catch the sunlight would boil that water, and they would use the boiled water to spin a turbine. Very clever design. The reason they don't use spherical mirrors is because you get something called spherical aberration. When you make them kind of big, the lines don't exactly cross. They don't exactly meet at the focal point. A parabola puts them more precisely at a single point. But for our purposes, we're using spherical mirrors, spherical lenses. Even though a lot of times we'll use parabolic mirrors to adjust for what's called spherical aberration. Aberration just means it's like a fuzzing of the image produced. All right, cool. Then we talked about ray diagrams. We made 4 different ray diagrams, 3 of them for concave mirrors, and 1 for the convex mirror. And then I gave you some equations that you can use. Any questions about any of the stuff we've talked about? Yeah.
Just really quick, this might be a dumb question, but for the equation, the image distance over the object distance, with the negative, if you have like a virtual image that already has a negative distance, do you do like negative so that it makes positive?
Yep.
Or do you,
And that makes sense because it was right side up, right?
okay, I didn't know if that was
Right side up means a positive magnification.
okay.
So it does work.
And then can we, for like an exam or a quiz or something, if we have to draw one of these, can we use like different colored pens? Because I'm looking at my notes.
Yeah,
It's
that's
this
fine.
one, it's so confusing.
Yep. Other questions? Yeah.
So when people like light a fire using a mirror in the sun, is
Yeah.
what's the actual thing that's lighting the focal point?
Yep. So the light rays coming in from the sun are,
I don't know, I was just wondering.
it's a great question. There's a legend of Archimedes making a death ray with a bunch of mirrors, right? The Mythbusters tried to do that and they found that they couldn't, it didn't work. But it's a fun thing to think about. And yeah, if you're using a mirror to light a fire, it's possible. I've seen people pop popcorn with a mirror in the sun. It's really neat. What they're doing is they take a concave mirror, they put whatever they're trying to heat up right at the focal point. So the light rays from the sun are so far away that they're essentially parallel coming in. Yeah, they're spreading out, but it's going from so far away that they're essentially parallel. The angle between them is tiny. So parallel rays, when they hit the mirror, come together at the focal point. So it's taking whatever energy it can gather from that area that it is encompassing and putting it all in a single spot, a single point in space, and that heats it up enough to pop popcorn or light paper on fire. The problem with using a mirror to do that is that usually when you put something in front of the mirror to be at the focal point, it blocks some of the light coming in. So that's why magnifying glass actually works a little bit better, a converging lens. But we haven't talked about that yet. I do want to talk about refraction just a little bit because that's what we're going to continue on. And you're going to get a whole bunch of it tomorrow when you talk about lenses with Dr. Treese. I told you light can bounce off of stuff, or it can pass through stuff, or it gets absorbed by stuff. Bouncing off of is reflecting, and that's what we've been talking about most of this time. When it passes through, that's called refraction. And refraction is the bending of light. You guys ever push a push lawnmower? Mm-hmm. You ever push a push lawnmower like on the driveway, and then when like part of it gets off in the grass, that part slows down and it kind of pulls? Another example, you ever drive here in the wintertime and get a little too close to the edge of the road in the slushiness on the right-hand side? Have you ever had that happen? It's kind of scary. If you've ever had that happen, it's scary because your car tries to go into the ditch. Why? Why does your direction change? Because what? It kind of, well, what it's doing is slowing you down. And it feels like it's pulling you. But when that front right corner of your car slows down and the rest of you speeds up, it causes you to change direction. A change in speed results in a change of direction. And the same thing happens to light. When light passes from one medium to another medium, the speed of light in that medium is different. And when it slows down, it bends. When it speeds up, it bends. The same as when you're pushing the lawnmower or when your car gets to the edge. Another way to think about this, and probably a more physics accurate way to think about this, is light behaves in such a way that it takes a minimum amount of time to get from point A to point B. The optimal optical path length minimizes time. No, I'm not saying it again. You don't have to write that down. I'm not going to quiz you on it. But what does that mean? If I'm at the beach and there's some hard ground, there's some sand, and there's some water, it's much easier for me to run on the hard ground than it is for me to run on the sand. If I want to, it's really hot. I want to get to the water as fast as I can. Minimum amount of time. Do I spend more time on the hard ground or more time on the sand? Where I spend more time where I can go faster. So I have a kind of a big angle here on the hard ground and a small angle here as I cut across the sand. Light does the exact same thing. And I can show you. I'm going to show you. Okay, I've got light moving through air. When light moves through air, it moves at essentially the speed of light, c, 3 times 10 to the 8th. And I've got a piece of plastic. This piece of plastic slows the light down. The light wants to go this way. I put the plastic there, and it changes direction. Can you see the difference in the angle when it's in the air versus when it's in the plastic? That's called refraction. The ratio of the speeds at those two different things determine how much the light bends. That's what we're going to pick up on Friday. You're probably going to know a whole bunch about it from the lab, though.